have divided my presentation into two parts. In the first part, we will deal with the materials which we usually utilize in terms of design and construction. Well, the second part, we will detail of the process of designing a particular building. Now, for the sake of this presentation, I'm restricting myself to material of reinforced cement concrete because in our country, the construction in steel is still not so common. And that is on account of number of reasons. Even though structural steel can be considered as an extremely versatile material, but still the usage of structural steel in our country is limited to a very large extent. There are a number of reasons that why you will find that the structural steel is not being used, but that will become a topic of another discussion and on a different forum. So today what we will do that we will restrict ourselves to reinforced concrete, its material, what as an engineer we need to look into the properties and how to make the best possible. We are talking about the design basis report. We will make due references to various Indian standard codes that we need to comply with. As I had explained initially that we will restrict ourselves. Hello. Okay, we will restrict ourselves with the concrete and reinforcement. For the sake of formality, we will define concrete, that concrete is a mixture of cement, fine aggregate, coarse aggregate, which is mixed with water and obviously air. And then, of course, nowadays the concrete is not complete without the mention of admixtures. The admixtures have become integral part of the concrete, and that is essential because, you know, when I started working, say 40 years before, admixtures were hardly used, except for, you know, we used to use certain elements for a quick setting concrete. Organizers, I'm getting some disturbance. Is it possible to unmute people? Because, you know, the host can mute the rest of the guys. Thank you. So when we talk of concrete, we make it into three parts, or we will go step by step. That when you add water to cement, we get what we call as a cement paste. That cement paste, when it is mixed with the fine aggregate, you get a second stage element that is usually called in our engineering fraternity as mortar. And when this mortar is combined with the coarse aggregate, obviously it takes the form of a concrete. So we use all three materials in different forms. Only cement and water many times is used for purposes of grouting. Cement paste and fine aggregate is used other than structural issues such as bedding material, rendering material like plaster, bonding material in the masonry. While once we add a coarse aggregate to it, we start getting the structural concrete in place. The usually available cements are ordinary Portland cement. These are Portland cements which are called actually the hydraulic cement. Now, when we say that it's a hydraulic cement, it means that when you add water to it, it will create an exothermic reaction. And that exothermic reaction will harden the cement paste. Now, cement essentially consists of limestone, clay, and iron ore, which is blended and heated in a kiln to a temperature in the range of around 1200 to 1500 degrees centigrade. This clinker is then ground in a cement plant to the consistency of a powder, and the gypsum is added to control the setting time. Usually has a very fine particle, and the standard size is below 50 micron. The types of cement, I have listed them on my presentation. As I said, we ordinarily use ordinary Portland cement in most of the constructions. We tend to use sulfate-resisting cement, which is mentioned in the category D, where we are expecting certain attacks because of the chemicals present in air, like chlorides and sulfates. Then we get a slag cement, we get a quick setting cement, we get a super sulfated cement, which have its applications in different sets of atmospheric conditions. Now, what is the role of a cement? Before we go to the strength of the cement, let's understand that what is the reaction of hydration. Here, when I'm saying C in the equation, C means CaO, S will denote silicon dioxide, SiO2, and H is obviously H2O. So there's a two-stage reaction, that the reaction which is given on the slide itself, and both the reactions are supposed to create CSH gel. This CSH gel is considered to be your cement, hardened cement paste, which will impart this strength to concrete. We will dwell in detail slightly later. Now, when the cement arrives on site, you need to ensure that the cement is complying to the standards required. So we do the field testing by even taking it in hand, the rubbing it, then trying to see the heat of hydration. A simple method is that you take a fistful of cement in your hand and then dip your fist with the cement, dry cement, into the bucket of water. And what you should feel is a heat of hydration. That means you feel a good amount of warmth in your hand when you have immersed that cement into the water. That will ensure that your cement is capable of giving excellent exothermic reaction. Obviously, in the laboratory, we need to check the fineness test, standard consistency test, setting time limit tests, strength tests, so on and so forth. Most of the Indian standard codes will give you these number of tests. Just for the sake of clarity, I have given the VICAT apparatus, which is usually used to test cement. Then we talk of coarse aggregate. Now, the coarse aggregate is the one, along with the cement paste, which imparts strength to concrete. And usually, by weight, the content of coarse aggregate would be in the range of around 40 to 45%. The standard definition of a coarse aggregate is all the aggregates which are bigger or larger than 4.75 millimeters in size. Obviously, there will be restriction on the upper size limit. When we say 20 mm downgraded architect, we will say that the maximum size of the aggregate will be 20 mm. If we say 40 mm downgraded aggregate, that will mean the maximum size will be 40 mm. In most of the structural concrete that we tend to use in buildings, we have what we usually call it as 20 mm downgraded aggregate. That means no particle size will be bigger than 20 mm. Of course, the Indian standard allows to the extent of 5% to be bigger than 20 mm, but that's a kind of a variation. Usually, the standard size of particle would be 20 mm and not less than 4.75 mm, which will be classified as coarse aggregate. Now, this is usually known as gitti or khadi in Marathi. The most important feature of a coarse aggregate that one has to keep in mind, that you need to observe the size and shape of the material. I'm not going through all the tests that are required to be carried out. Important part you have to bear in mind that your coarse aggregate should not be flaky in nature or too much elongated. Because what will happen that instead of getting a rounded aggregate or a squarish aggregate, which is very difficult to get, if you get a flaky material or a highly elongated material, then the shear failure during the loading of the concrete will be inevitable. And when you will have the concrete failure, it may not be by the mortar failure, but it will be by the aggregate failure. And we certainly do not want the concrete to fail in aggregate shear characteristics. So we need to entirely avoid flaky aggregates while using it on site. This you must have seen, this is called as sieve analysis. In order to define the size of the aggregate in terms of coarse aggregate and fine aggregate, we use these kinds of sieves usually on site. There are a set of sieves which start from 40 mm, 20 mm, then 12 mm, then 4.75 mm, then 2.38 mm downwards. So that means you classify the aggregate depending upon size. That means the finer aggregate will keep on passing through the various sieves. And on the right side of that slide, you will find the set of sleeves which are used in testing the coarse aggregate and the fine aggregate. These are the grading limits given in IS 383. One who desires to do career in the concrete technology and mixed design in particular, this IS 383 will form the basic foundation for the coarse aggregate, and then you will have to select your gradation of the aggregate depending upon this table. I'll come to fine aggregate. Fine aggregate is what we usually call it as sand, and that will be between 4.75 mm. My slide doesn't contain the minimum size. Usually the size will be between 4.75 mm to 150 micron. Anything lesser than 150 micron, the quantum of that particle size, which is below 150 micron, will have to be limited, and it should not be more than 7 to 10%. Usually, because that will form otherwise, that will come in the form of a stone dust. So we will have to necessarily control the particle size less than 150 micron. These are the grading limits, again specified by IS 383, and these are the grading limits for all. Saying all in aggregate, it means the fine aggregate and coarse aggregate put together. So these are the limits which have been specified by the IS code. The reason I'm talking all about this, that my observation in the field is that the best of the structural engineers tend to disregard the material properties of the concrete because they believe that it is best left to the site engineer. It should not be done so, because finally, whatever best design you might produce, if you do not pay attention to the quality of material that is getting used and the way in which it is used, the end result will not be desirable. So most of the structural engineers and civil engineers working on site will have to be acquainted in terms of concrete quality and the concrete theory, because nowadays people have started saying that what is being taught in college is not utilized in the field. No, it's absolutely wrong. We tend to forget what is taught in the college, and we tend to carry an impression on site that practical field is entirely different. No, honestly, when you will marry the practical field with the theoretical study that you have made, then it will render excellent results on site. And we usually tend to use two kind of terms. One is a poorly graded aggregate, and second is the well-graded aggregate. It is very simple that if you have only coarse aggregate and the cement, there will be a lot of gaps left in between which are filled by the cement paste. And obviously, this will weaken the concrete matrix for the shear failures. So if these gaps are filled up with the fine aggregate, then obviously you will have a dense concrete, and that's where the grading of the aggregate, which I had shown in the earlier chart, will come in picture. And that's why when we say that we want excellent compact concrete, we need to emphasize on having well-graded aggregate pattern in our concrete. These are the various equipment that you will find in laboratory for testing of the aggregates. I'll come to one more chapter. I'll tell you, I'll be very honest with you that till 2000, in India, hardly we were using any mineral admixtures. Now, Sandip Polytechnic comes from Nashik. So Nashik is the basic source for the fly ash, which is produced as a byproduct in the thermal power plant. It comes out of an electrostatic precipitator, which are now fitted to the boiler outlets. And this fly ash was considered as a waste material till 2000. But it has a fantastic advantage when it is properly and scientifically utilized in concrete mixing. Now, these are the various mineral admixtures that we tend to use in concrete nowadays. These are fly ash, then metakaolin, silica fume, GGBS, and so on and so forth. Now, what is the use of mineral admixtures? Let us understand one thing. It started as a mineral replacement or a cement replacement. So people started thinking in terms of that, look, I have got a cheaper material by which I can replace cement and still I will not lose the properties of the concrete. As a matter of fact, if you study the theory behind this, you will understand that mineral admixtures have now become part and parcel of the concrete mix, which will render a durable concrete. As a matter of fact, I will go a step further and say that ideally, one should now avoid using only OPC cement, and OPC cement will have to be blended with one of these mineral admixtures. Why? We will see it in the next slide. So this is a pictorial presentation that how fly ash will be there. The replacement could be in the 5% to 50%. These are all spherical particles, and these act as excellent void fillers. Now we talk of silica fume. Silica fume is a much finer material, and this is usually used when we want to get a higher grade of concrete. That means fly ash would be good enough for concrete up to M30, M40, M50 grade. But if you want to go to a higher grade like M60, M70, M80, and if you want to gain that strength by controlling the cement, because as you all are aware, we are not allowed to go beyond 450 kg per cubic meters as a cement content per cubic meter of concrete because of obviously shrinkage problems. In this case, the silica fume will come to our help, and with the same content of cement, because of the reaction that I will explain further, we are able to get a much better strength. This is another class of mineral admixture. This is called as ground granulated blast furnace slag. This is a byproduct from the steel furnaces. This was also being treated as a waste material in the initial period, but this has the same properties or similar properties, let us put it that way, like fly ash, that they tend to enhance the quality of concrete. So these are various pictorial descriptions of how these various GGBS elements will tend to mix with the concrete. Now, friends, please pay attention to this slide because this will explain us that why we need to utilize the mineral admixtures. The basic chemical reaction of when we add water to the ordinary Portland cement, you get a CS gel as we have seen in the first slide, and then we get a primary subproduct as calcium hydroxide, that is a plain lime. Now, if you have seen that whenever we are not using these admixtures, and if you see a kind of a strengthened concrete or a dry concrete, you will find leaching in the form of certain white material coming out of a concrete after 3 weeks or 4 weeks. This is exactly the calcium hydroxide which tends to come out of various voids left in concrete. Now, this lime eventually comes out and then it vanishes over a period of time and it leaves voids or pores in concrete, which makes concrete porous. Now, what exactly will happen if the concrete becomes porous? Because then that will allow the water or the moisture and other gases to enter the concrete. Now, in a place like Mumbai, see, in Nashik and Pune, we are comparatively better placed because we do not have saline conditions. We do not have sultry conditions. We do not have chlorides or sulfates in air. But in the coastal area, in a place like Mumbai, in a place like Calcutta, in a place like Chennai, where the chlorides and sulfates will be there in air, these chemicals tend to enter through these pores. And this air entrainment with the chemicals eventually starts corroding the reinforcement. within the concrete. Now, this reinforcement, when the corrosion starts, as everybody knows that the reinforcement under the case of rusting will expand in its volume. When it expands in its volume, it will start exerting pressure on the bonding concrete. So what it will make that the bonding concrete will develop further micro cracks. These micro cracks will make that concrete further porous, thereby allowing further air entrainment and thereby weakening the concrete. Now, how do you stop this? That means now we will have to utilize this calcium hydroxide, which has come as a byproduct of the primary reaction in some different method. So what we do, that we use these mineral admixtures. These mineral admixtures essentially contain amorphous silica in the form of SiO2. So if you see the reaction at the bottom, this calcium hydroxide in the presence of water will react with SiO2, which are the silicates present in the mineral admixtures, and that will form a secondary gel. Now, this secondary gel will actually replace the calcium hydroxide, and it will kind of create a further compacted concrete. That means we will have virtually non-porous concrete, thereby making excellent quality of concrete, which will not allow any moisture entrainment or any gases entrainment into the hardened concrete. And that's why in places like UK, in the coastal areas, you are not allowed to use ordinary Portland cement concrete. You need to have a blended cement concrete. When I'm saying blended cement concrete means you will have to blend either fly ash or GGBS, or in case of a higher grade of concrete, silica fume along with the cement to make the concrete impervious. And this is the most important that we need to bear in mind, that please make judicious use of mineral admixtures like fly ash or GGBS. Not only it will save your cost, but also it will make your concrete of a much better quality. Now we will go to further admixtures, that we will have different shrinkage reducing admixtures, water reducing admixtures, foaming agents. That application you will understand as and when you will go with some special kind of concrete required for equipment foundations, required for certain amount of grouting, required for certain amount of high criticality turbine foundations, so on and so forth. Now we will briefly touch upon the reinforcement because we have touched upon the concrete. Now, concrete, as you all of know, that it's good in compression, but in weak in tension. So obviously, when we are creating a concrete, reinforced concrete element, we need another element which is strong in tension and shear. And that's why this is kind of a composite material that we are using in the form of RCC. All of you know that reinforcement comes in two different types. When I was in the college in 70s, we didn't have high yield strength bars. Possibly I did all my education in mild steel plain bars. While I was just finishing education, the HYSD started coming into the market, and that was always of the grade of Fe415. But now we are fortunate that we are getting grade of concrete up to 500, 550, and 600. Now, you also need to understand that all of a sudden we should not start using 600D, because if you are using, see, this 550D for 600D will mean that we have the yield strength of 550 MPa or 600 MPa. But to have that matching 550 MPa or 600 MPa, we need to utilize it with the high grade of concrete. Please do not use 550 grade or 600 grade with the low grade of concrete like M30, M35, M40. If you want to go to 550D, for the strain compatibility, you need to ensure that you are at least going to M60 concrete or M70 concrete. And secondly, what you need to remember, also, if you have seen, I am mentioning rolled steel members like angles, T-sections, channels. I am purposely doing this because the time has come that we do not depend only on reinforcement, and now we call something as a composite construction. wherein along with the reinforced concrete, we also embed the H sections, C sections, I sections into the concrete, because that makes the concrete section much stronger with the introduction of these road sections. When we want to restrict the sizes of the concrete columns, concrete shear walls, and when we are in a high-rise building wanting a very high capacity in terms of shear as well as compression, we tend to use composite sections, wherein these structural steel members are utilized in conjunction with reinforcement as well as concrete. While we are using the grade of steel, we have to also bear in mind that when we are using for Fe 500 and above, in order to retain the ductility, we have to have the percentage elongation of at least 14.5. Because IS 1786 says that for Fe 500, the acceptable percentage elongation is 12%. But when we have to design the structure in the seismic areas for the ductility requirement, our strength, our percentage elongation has to be 14.5% minimum. So that is something we have to bear in mind. And usually it is rendered by this thermomechanically TMT category, thermomechanically treated reinforcement. It's a different metallurgical treatment, but which will give you higher percentage of elongation. So this is brief touchdown on the materials part that we essentially, as a designer, we need to know. Obviously, today I'm not going to concentrate anything on the construction aspect. I am going to restrict my presentation to the design aspect, and that's why in the materials part, I have dwelled upon only the properties of the material that we have to bear in mind in order to fit into the correct design procedures. So what I am doing, that all of you must have gone through various IS codes or must be in the process of going through various IS codes. So I am not making a particular reference to IS codes, but I am referring to all the IS codes together when we take a particular design of a building. Now, for the sake of example, I have picked up one of my projects where the design is in process. And you will ask me that why this? As I said, I have purposefully picked up a building which is 240 meters high. Obviously, I know that not everybody will get to design a building of this kind. But if your horizon is wider, that means if we start thinking in terms of tall buildings in the first place, then you will start thinking on various different aspects of the design much more purposefully, because a smaller building, a shorter building, a building of 6 stories or 5 stories might not have so many complications. And there you will say that, oh, why do I need to create a dynamic analysis? Why do I need to create and go into various details? But there's no harm. Let us know that what is needed to be done for the top of the end buildings, so that it is very easy to tone it down to a lower building. So I'm just setting forth an example of what a 240-meter building requires as a minimum standard to be followed when you are proposing to construct that building. Now, these are the minimum standards that we need to comply with when we are designing the building. Now, I will go one by one. Of course, IS 456 is our basic foundation code, which deals with the RCC, that means reinforced cement concrete for the structural use. All of us are well acquainted with it. Our next is IS 875, Part 1, Part 2, and Part 3, and Part 5. All of us know that when we are talking of a building, obviously the building, why we design, why we put a strength of concrete, why we put reinforcement, because it is subjected to inertia forces. It is subject to gravitational forces. It is subjected to lateral loads like seismic and wind. So we need to have standards which will define various loadings that we should adopt. So there are various loading standards. IS 875 Part 1, that will give you the unit weights of each building material. IS 875 Part 2, which will give you details in terms of the imposed loads, or what we commonly call as the live loads. Then 875 Part 3, will give the wind loads, which the tall buildings are required to be designed for, and the part 5, which will give the spatial loads. So these are the 4 important codes that we need to go through. Then the most important and most talked about code is IS 1893, which is Earthquake Resistant Design Structures Code. Now, this has been revised just a couple of years before. The old version pertained to 2002, and now the new version, which is dated 2016, but which came into the hands of structural engineers in 2017, is the most important codes, especially when my friends are sitting in Nashik, because Nashik, Pune, Bombay are in zone 3, wherein all the requirements of seismic have to be taken into account. Not only the 1893 code, but all our structures will have to comply with the ductile detailing as specified by IS 13920. I'm not aware that the third year students would be aware of this code or not, but over a period of time, they will come to this. When I'm talking of a ductile, let us understand one thing, that what do you mean by ductile detailing? Ductile detailing is something that when we are talking of earthquake engineering, I'm deviating a bit because when I'm using the word ductile, the interpretation of ductility should be well understood. In a sense, when we are talking of a building which is to be designed for the earthquake codes, we have to bear in mind that earthquake engineering is not 100% perfect science. It's not 2 plus 2 equal to 4. What we say about earthquake engineering, it is a semi-probabilistic engineering. That means on the basis of various data collected over a period of last 200 years, we have come to certain parameters, assuming that you will get a seismicity to such a level. This keeps on revising over a period of time and depending upon various events occurring. To highlight this, I will tell you that we had a Koina earthquake in 1967. And Koina, which is in the southern part of Maharashtra, was in zone 2 at that point of time, as per the old code. Then subsequently, it was shifted to zone 3 of our 1893. Now, if you take further example of Latur, the earthquake happened on 29 September 1993. If you were to see the earthquake code of 1984, Latur was part of a peninsular part of India. And when I learned my engineering in the college, we were taught that the peninsular part of India is an extremely stable region seismically, in a sense that not a serious earthquake will ever occur. And we had 6.9 seismicity earthquake happening with a hypocentral depth of around 10 kilometers in Latur. So we changed our perception. And suddenly, Latur was shifted from zone 1 to zone 3. So that's why we need to also always bear in mind that our knowledge in earthquake engineering is limited to the experience that we have gathered. And of course, now with the remote sensing technologies that we have at our command, we are able to know much better in terms of subsurface geologies of the earth. So we are able to predict in terms of zoning. Just to highlight on this, I would add one more thing, that whatever zones we utilize, which we will see in the further course, that India is divided into 4 zones, zone 2, zone 3, zone 4, zone 5. Over a period of time, these zones will also disappear. And what we call as micro zoning will appear. With the help of remote sensing technology, the entire country will be divided into various micro zones. And in a place like Mumbai could be in a particular zone, but New Bombay could be in a different zone. Palghar could be in a different zone. And Palghar and Mumbai geographically are not more than 80-90 kilometers apart. New Bombay and proper Mumbai is not more than 60 kilometers apart, but they might have a different seismicity indices. So that is something we have to bear in mind, but that is for next 5 or 7 years to come. Okay, going back to the next course, that is all about ductility. Then 16,700 is the most recent code which has come about in the tall building engineering. For the first time, the Indian standards have defined the term as a tall building. The tall building has been defined as a building which has a height of 50 meters or more from the foundation level to the top. Please bear in mind the foundation level. It is not from the ground level. It is from the foundation level to the top. And then we have subsequent codes like 1786, SP16, these are the design aids, SP16, SP23, SP24, 34, these are the design aids. And we will see that these all books come to our help while designing a building. Now, what do we do? That when you get a building, now I will just skip this slide and go further. Now, this is a building that I'm talking of. This is a building, this is a floor plan. So when you get an architectural plan in your hand, in the first place, you will have to sit down with the architects and the clients and decide on the column locations, on the shear wall locations, on the core locations, on the size of the approximate sizes of the walls that you can think of. At the same time, you will have to utilize your structural judgment that where you would need the locations of the beams, how you would intend to frame the slabs, how do you intend to frame the building to resist the gravity loads and the lateral loads. And this is something which has to be done in tandem with the architects and the clients. And this is what I call as a framing plan. Now, such framing plans are prepared for every floor. And then you will have to create a description. So that's why I will go to the earlier slide, that you will have to define the building. If you see the functional requirements, that means this building is now giving details that it has a one basement floor of particular height, then a ground floor, then a first floor, then second floor of different height, which is used as a service floor. Then there are third to 44th floor, which are typical floors, residential floors. Then there are fire check floor. There are different clubhouse floors. So when I'm saying that I'm preparing a statement, your statement per se should be able to speak or give a volume of the data in terms of that building. So this is something which is essential to be created so that anybody as a third party going through your design basis report is able to visualize a building. So this is the framing plan that we talked of. This is just for the information sake. This is the stacking plan, how the building will look in the section. And this is an architect's view in terms of its perspective. No, these are the design criteria. Of course, as we had talked about materials, in the design basis report, you will have to specify the kind of cement that you intend to use, the aggregate that you will intend to use, what is the maximum aggregate size that you will employ, then what are the admixtures that you intend to use. Because, you know, for a building of this nature, your grade of concrete will be M70, as you see on the slide. Now, for M70 concrete, the correct selection of the mineral admixtures as well as chemical admixtures is most important. And that's why you need to examine the appropriateness of the admixtures that one will utilize. And that mention has to be made in the design basis report. And the reinforcement grades also, because here you will have wide choice. You are talking of a very tall building, so you can go from FE 415, FE 500, FE 550 to FE 600. So here we had made a choice of using 550 and 500 grade of materials. And that is something we will list out. Now, obviously, the problem will come. So far, we have not talked about foundations. And I will just briefly touch that a builder will have a very high capacity requirement in terms of the safe bearing capacity from the soil. And unless you have an extremely hard rock, which is able to give you capacity in the excess of 200 ton per meter square, otherwise you will be required to go for piles. Obviously, this building that we are designing in Delhi, there's a lot of alluvial deposit. So there is no question of getting a hard strata. So we had decided to go in for piles. So we have defined the piles, the reinforcement, the link beams and the shear walls, and the floor-wide distribution of various grades of concrete also can be shown. Again, I'm emphasizing that this design basis report is most important because this piece of paper or this documentation will speak about the details in terms of thoughts you have given in terms of designing a building. That means somebody who has not been part of a design team, if he has been handed over this document, he should be able to visualize the way in which your thinking process has gone about. Now, this will give you various column elements and the serviceability conditions and the exposure conditions. So what are the nominal covers that we are adopting, and what are the exposure conditions that we are talking of? And the fire rating is most important. That is one part which was previously being ignored, but now in emphatically now included in all design basis reports. With so many frequent unfortunate incidents of fire, your fire rating of a concrete element is most important part of your design basis report, and that is something you should always include and pay an adequate attention to that. This is some minimum percentage of the reinforcement that we will employ in our elements. And now we will have to create a node that when we are designing a building, you will have to create some kind of a node. Of course, I have not burdened this presentation with the kind of node that we prepare, but what I'm saying that we will need to prepare a clear note on the philosophy of the structural framing. That means the way in which we have visualized this building will resist. As I have been taught in my early years, it's very easy to design a building. Somebody who understands how a building will fail for a given loading condition, if he knows the mode in which the failure will occur, the job is very simple. You need to strengthen those portions which will become critical or which will become a weak link. Those weak links you will have to eliminate. So your structural framing will have to be done in such a way that you are able to establish a very clear load path without any unnecessary gimmicks, so that the gravity loads are transferred from the top to the foundation. And not merely gravity loads, I'm talking of the lateral loads also. Here and after in my presentation, when I'm talking of lateral loads, we have to keep in mind that I'm talking of either earthquake load or seismic load or wind load. Obviously, we will not assume seismicity and wind event to act together. So it is either or. That means either the structure will be subjected to seismic load or structure will be subjected to wind load. So that is something we will have to establish a clear load path. All my friends have to bear in mind the importance of establishing a clear load path, and you will have to establish that during this load path, there is no vulnerable element which will go into secondary deformations or tertiary deformations, which you are not able to account for your analysis. That is something, and if that is to undergo a secondary deformation, then your analysis should clearly account for the effects of those secondary deformations. That is something we have to bear in mind. Then obviously the next step is that now hardly anybody does design with the hand calculations. So many commercially equipped softwares are utilized, like STAD Pro is there, ETAFS is there, ANSYS is there. So you need to define which software you are trying to utilize, whether you are going in for a 2D approach or a 3D approach. That is something you will have to mention. And then when you are making a numerical model, there are a number of assumptions here that you make. So you need to list out clearly the assumptions. For example, you might create certain crack sections. You might create certain releases. That means you might say that this beam, even though it is supporting on the two primary beams, I'm assuming that to develop a rotational capacity. That means I will make that element as a pin jointed element. So all those assumptions you need to clearly kind of enumerate in your design basis report, so that again the clarity in terms of analysis philosophy is established. Obviously, as I said, we need to design the building for the gravity as well as the lateral load and the temperatures load. And usually what we do that for the sake of correctness, because each floor will be subjected to different kind of loading. Your parking floor will be subjected to different live load. Your commercial floor will be subjected to different live load. Your residential floor will be subjected to different live load. Your workshop floor will be subjected to different live load. Your service floor will be subjected to different live load. So every floor wise, you will have to enumerate the kind of loading that you have assumed. Now for that, obviously I'm just skipping a couple of slides, and you will have these tables to take help of. This is IS 875 part 2, and they have detailed so many different types of buildings for which different class of loading is given. These are the different classes of loading which have been given. So you have to refer these clauses and then appropriately select the applicable loading standard to your building and then adopt them in your design calculations. So this is something floor-wise presentation of the live load. Now there will be three types of gravity loads. One will be dead load. Obviously that will be on account of the self-weight of the elements that we are using. Now second, what we call is a superimposed dead load. What is superimposed dead load? Superimposed dead load is kind of a filling that we make in a toilet block. You know that the toilet floors, we leave it sunk, and then we do the waterproofing, and then we fix the fixtures and then fill it up. So your toilet loads could be higher. There could be a 200 millimeters of filling. Now, assuming around 2000 kg per cubic meter or 20 kilonewton per cubic meter of loading, you will have to assume that additional superimposed dead load. If you have to fix granite or marble, your floor bedding could be of 75 millimeters. If you are fixing with a chemical, then your floor bedding could be only 20 millimeters. So your floor bedding also will give a different kind of load. A granite floor slab or panel would be of a different thickness. It could be 20 mm, it could be 30 mm. Your tile could be of only 10 mm. So this is called as the superimposed dead load, what we call as the superimposed dead load. And obviously live loads I have explained to you earlier. Now these are floor-wise presentations of the gravity loads. So this is what we are calling as the dead load, superimposed dead load and live load. Obviously then the slabs will have to be designed for fire tender movement, because you know most of the buildings have podiums. The fire tenders have to be allowed to be moving around to take care of the firefighting requirements, and those firefighting slabs are designed for much higher loads, and that is something which we have to always bear in mind, because that tends to get missed out, because architects and fire consultants do not specify the fire path, and that is something we need to bear in mind and ask specifically the architects that tell us the fire path, so that we are able to design those slabs for higher loads. Then 875 part 2 will always allow you the live load reduction. That means even though we are considering full live load, it is assumed statistically that all the floors, when building is complete, may not carry the full amount of live load. So depending upon the number of floors in the building, you are allowed to reduce in your calculation the live loads assumed. So these are the percentages of the live load reduction that you need to account for the optimal design of a building. Then when it comes to partition wall loads, you will have different kinds of materials. You will have conventional bricks, you will have lightweight bricks, you will have dry walls, you will have Shera walls. So you will have to define that what kind of material that I'm using. Now, when I'm using an ordinary brick, then I will also have to ask that am I going to do a normal new roof finish plaster, or am I going to do only gypsum? What is going to be the thickness of the plaster? So accordingly, I will have to utilize the loading pattern onto that masonry so that the proper load is accounted for. This is something we had referred to. So this is something we'll skip. So this is all about gravity loads. Now we will come to part 1 of the lateral load. We are going to briefly talk about the wind loads. For the wind category, this is part of 875 part 3 2015 code. The country is divided into various zones where the basic wind speeds are defined. For our consideration now, for Mumbai is in a zone of 44 meters per second as the basic wind speed. If you come to Pune and Nashik, that would be in the range of 39 meters per second. If you go to Bangalore, that could be in the 33 meters per second. So depending upon various wind data collected over a period of years, this is the wind climate diagram for our country as a whole. So this is the basic wind velocity for this project. Obviously, Delhi has a much higher wind velocity, which is 47 meters per second. Now, if you go through that code, there are various factors. This is K1 is called as the probability factor, K2 is called as the terrain stiffness factor, K3 is called as the topography factor, and K4 is called as the cyclone factor. That means these basic wind speeds which have been given by the code have to be modified further with the multiplication of all these four factors. So this is what we call as VZ, that gives you the maximum design wind speed, and it is achieved, it is kind of calculated by multiplying this VB, which was the basic wind speed, by VB into K1 plus K2 into K3 into K4. And then when you arrive at this maximum design wind speed, you get a wind pressure by this formula. PZ is equal to 0.6 VZ square. So this is the maximum pressure that you will get. And now this has to be further used in calculation with the effect of force coefficients. That means depending upon the geometrical configuration of the building, you will work out the various force coefficients, which are called as the CF. And these CF are worked out on this basis of these parameters. And then the basic wind pressure is calculated and it is applied throughout the height of the building. So this is something, the calculation of wind speed. Now, how do you do the analysis with this? In your StatPro model or ETAB model, you apply this on the exposed surfaces of the buildings in both the directions. That means on all four surfaces, you apply these wind speeds and then you analyze it through your numerical process. Now, this is all we are doing by way of a static wind speed, because what we had been working out, that VB, the basic wind speed, is on the basis of a 3-second gust, but that is still a static wind speed. Now, actually, the dynamic wind response also needs to be worked out, and this is not required for all kinds of buildings. For certain set of buildings, this is required to be done. So what we call the dynamic wind response is to be worked out for a building with a particular aspect ratio or a particular frequency of a building. Those details we will skip for the moment. Now, in case of a taller building, I'm just introducing a concept that in case of a taller building, these calculations of the coefficient of friction, that is CF factor, and the gust or the dynamic response, it becomes too approximate because the buildings are not necessarily rectangular in nature alone. Buildings can have different shapes, different sizes. So what we do, that for a building of this nature, we go to the wind tunnel. This is something extension of an aeronautical engineering. That means we create a building model in a given material. These building models are usually created to a scale of around 1:300 to 1:400, and they are placed with by modeling the surrounding proximity analysis. That means we also create surrounding obstructions in the form of a small dumb models of the building surrounding, and these are placed in the wind turbines. And then these wind turbines have a capability of creating the wind speeds of the desired pressure, and these are created at different angles. That means if you consider a 360 degrees pattern, that means if this is 0 degrees, this will go on creating wind at different angles. That means this is 10 degrees, 20 degrees, 30 degrees. That means if this is considered a quadrant 1 in our XY coordinate system, this is quadrant 1, this is quadrant 2. So we create at every 10-degree interval different wind pressures through a wind velocity of a equivalent to basic wind speed, and then through the instrumentation on that building, we measure the responses of the building. This is called as the wind tunnel study. At this stage, it is easier and better to keep in mind that in case of a complex building, mere codal compliance is not sufficient, and you need to take up the wind tunnel studies for a more complex building. Now, what it will give, these wind tunnels will give you these forces. Now, these forces will be given as the maximum forces. If you see that they will give a max force envelope at a given angle. That means this load case 1 is maximum when the wind is flowing at a 260-degree angle in that circle that we had seen. And what it will give you? It will give you Fx, Fy, and Mz. That means force in X direction, force in Y direction, and this is torsional moment about the vertical axis. Now, this is usually not obtained through your codal compliance. And this can be obtained because this is the most critical parameter, and this can be obtained only through the wind tunnel analysis. That you have to bear in mind, that in your normal numerical E-type calculation, this figure is not available. And this is the most important figure to understand the behavior of a building against wind. And then these are various accelerations that we have limits on. That means when the building is subjected to wind, it is not so much as the strength, but the serviceability criteria which come into picture, wherein people perceive certain motion. That means in case of an extreme wind motion, people feel the swaying motion. In an extreme, now we had Amphan kind of cyclone which struck East Coast just last month, where the wind speeds were in the range of 135 to 150 kilometers per hour. And there people experience swaying motion at the top levels in a tall building. Now, these are giving various accelerations. These are the accelerations actually which are allowed for a 1 year return period, for a 5-year return period, for a 10-year return period. These are part and parcel of various international standards which we have to comply with. Now, this is about wind. I know I'm on to the last leg, so another 10 minutes I will take. We will talk of the earthquake. Now, in Nashik, Pune, Mumbai, we are sitting in zone 3, so which is the seismically active zone. And as I had mentioned earlier, in this seismic active zone, it is not only essential that we need to have our design compliant with 1893, but we'll also have to compulsorily comply with the ductile detailing conditions. Now, I was trying to explain the ductility. The ductility to a structure is imparted by the reinforcement placed in the concrete, and also the configuration of reinforcement or method of placement, the way in which you strengthen your joints. The ductility is defined as the capacity of a structure to deform under seismic conditions without reaching the collapse. That means when I was saying that we are talking of a semi-probabilistic event, that means we do not know to what extent we will have a damage. But we need to ensure that our building has to be designed in such a way that in case of an extreme event, the building might suffer damage, but building will not suddenly collapse. That means the occupants of the building will have adequate time to escape during that earthquake or during or after that earthquake event. And that's what we call as the ductility of a building. That means the building will have to be adequately safe so as occupants are able to escape from that building within the reasonable amount of time. And that is mandatory where we are living in zone 3, zone 4, and zone 5. Now, as you see, the Indian map is divided into 4 zones. If you see the green map that you are seeing is zone 4, then this is yellow is zone 3, blue is zone 2, which is seismically less active. Zone 1 has been abolished after 2001, and all these orange colors are in zone 5. These are the extreme zones. Now, obviously, in the textbook, you must have learned that what we do in our seismic engineering is a force-based design. Even though earthquake is a deflection-based activity, that means actually in case of a wind, it is the force which is applied which creates the forces in the building. It is the external wind force. In case of an earthquake, we need to remember there is no external force. What happens is the displacement of a building. When the earthquake occurs, your soil starts moving. When the soil starts moving, it displaces the foundations which are resting on the soil. And those displacements create inertia forces. But to make our theory simpler, our codes have employed till today a force-based design. That means we define the seismic force for which building is needed to be designed. So now that force is defined by this formula. Obviously, this is all clear to everybody, by which we work out the base shear, what we call as a VB, which is this AH coefficient multiplied by the seismic weight of the building. I will not go into the details of how to work out the seismic weight. Obviously, these are the minimum earthquake horizontal forces that which we have to make applicable. This is a new addition to the structure in the sense that means if you are in zone 3, your seismic force will have to be minimum 1.1% of your total seismic weight. That means if your seismic weight of the building is 1000 kilonewton, then you will have to have 1.1% of that 1000 kilonewton as the horizontal seismic base shear which is made applicable. Now, obviously, the importance factor is second important thing where the revision has happened. And previously, we used to design all residential buildings for an importance factor of 1. That means we didn't have any magnification of importance factor. But now, for all residential buildings also, which have more than 200 occupants in the building, we need to design this building for an importance factor of 1.2. That means the new code has enhanced our seismic force by 20%. Now, these are the various response spectra that we refer. This is a spectra for the equivalent static method. Well, this is what we utilize usually in our ETAB model. This is the spectra for the response spectrum method. And these are the intensities, as I said, Nashik, Pune, Mumbai are in zone 3. So this is 0.16, which is called as the moderate zone. And this is the factor which will be made applicable. And you will have to do and establish all these calculations. That means you will have to work out the time period of a building. The time period of a building is worked out in 2 fashions. One is by the numerical methods, wherein you will work out the dynamic time period. And second method is given, which is the code-based method. That means the code-based method is something like this, that you need to work out the time formula on the basis of where you have shear walls on the basis of this formula. So on this basis, you will have to work out the time period. As you know that the lesser the time period, higher against, if you see on this graph, the time period and SA by G, that is spectral excitation, are inversely proportional to each other. So higher the time period, the lesser is the force, and lower the time period, higher is the force. So you will have to design the building for minimum of the 2. That means this is what we call as the static time period, and whatever our ETAB analysis will give us is the dynamic time period. And you will have to design the building for the minimum of the 2 values of time period, which is the maximum of the base shear. Now you will have to properly select the response reduction factor. This response reduction factor is most important in terms of the behavior of the building. For the buildings with the shear walls, as we have proposed, the response reduction factor is 4. If you have completely moment resisting frames with the shear walls, the ratio will be 5. And if you have a flat slab building, this response reduction factor will be 3. That means your seismicity will be higher. So you will have to do all these time period calculations, and then you will get a dynamic analysis, wherein you will have to establish your first 2 modes to be in translation. And thereafter, you will get all these. These are the story stiffnesses plots that you will get. And this is the story shears distribution. I'm just explaining this because, you need to examine this very carefully, that there is no untoward or irregular distribution in terms of the story shears. Or otherwise, we have to bear in mind that we have made some mistake in calculations or building is not correctly framed. That is something we have to bear in mind. Possibly for want of time, I am not able to dwell much in details, but I'm just highlighting the points, that these are the points that you need to take care of while you are designing a building. So these are various story responses. I believe this is now 5:20, and possibly I have covered whatever I wanted to cover in the right amount of time. So this is in general, when I'm trying to design a building, I would look into the basic parameters that we have to pay attention to. So here I complete my presentation. I say a big thank you with a question. Any questions? If the facility is there for the question answer sessions, I would welcome it right now. Thank you very much.
Okay. Thank you very much, sir. Very nice session.
I hope it was not boring.
Yes. No.
So how do we go about it? Do you have any question answer sessions?
Okay. So participant can ask question. First of all, those who want to ask the question, raise your hand or put it in chat box. Okay. No question. Okay. Okay. Uh,
As I see, some 30 people have raised their hands. I don't know whether they have a question or what.
Sir, first question: how we will calculate the time period of structure?
How do we work out the time period of a structure? Okay, as I said, there are two methods that when you model the given structure in either ETABS or StatPro, wherein you define the elements like columns, beams, shear walls, the program generates the time period for a given building. And that is something what we call as the dynamically calculated time period. I will take you just to the presentation. This is the modal participating mass ratios. This is the mass ratio. Now, if you see, I will just try to enlarge it if I can. No, I can't. If you see, this is the time period given for the first mode. I don't know whether this is clear. The time period is given in the first part. So this is called as the program calculated time period or the dynamic time period. And for various modes of the structure, and you need to carry out the analysis, which will take into account 90% of the mass participation. So the time period is given over here. And other than that, there are three formulae given in the code. One formula is for structure having no infill walls, only moment resisting frames, and that time period is given by 0.075 h raised to 0.75. That is the first formula. That is for the structures having only moment resisting frames without infill walls. The second formula, which is given for the structures wherein you have combinations of the moment resisting frames and the shear walls, that is given by the formula time period is equal to 0.09 h upon root d, where h denotes the height of the building, while d is the depth of the building in plan in the direction of the force. And the third formula, which I have mentioned in my presentation, when the structure comprises basically of the shear walls. So this is the third formula. So depending upon your type of structure, you need to work out. And this is something what we call in the common language as the static time period of a building. So these are the two methods. And you have to, as I said, pick up the minimum of the two, the static time period or the dynamic time period. Needless to say, the static time period is always lower than the dynamic time period.
Okay, thank you, sir. Next question is why we are not considering wind load and earthquake load at same time?
Oh, that is, it is assumed, conventionally it is assumed that the two natural occurrences will not happen at the same time. That means the severe wind conditions and severe earthquakes are statistically and probabilistically most unlikely to occur at any point of time. So it's a standard convention adopted world over that a severe storm and earthquake will not happen together. And that's why the events are considered in isolation. That means either earthquake at a given point of time or severe wind at a given point of time.
Okay, nice, sir. Next question: what time period we have to use for masonry wall?
What time period you have to use for masonry walls? It's difficult. You will have to kind of model the masonry walls with the proper modulus of elasticity. But the problem is going to happen when you model a masonry wall. There are going to be windows and doors as a part of the masonry wall. And those doors and windows have to be modeled properly, because if those are not modeled properly, then the problem will appear that you will get into erroneous calculation of the time period. Now, when you have to work out the building time period, that means RCC frame with the masonry wall, IS 1893-2016 has given a methodology to work out. So if you go to that particular clause, they will give you a method to work out the time period of the given building.
Okay, thank you, sir. Next question is which software is good for structural design, StatPro or ETAB?
Both are excellent. Both are excellent.
Okay. Okay, sir. Next question. while considering the dead load, percentage of shear wall with respective perimeter.
No, can you come again? Can you slightly elaborate?
While considering the dead load percentage of shear wall with respective perimeter. Question.
I'm not getting the question, honestly.
Question is incomplete, sir.
Yeah.
Next, how can we assume the type of slab, whether it is one way or two way, for irregular slab in StatPro as well as in manual calculation?
See, let's understand one thing, that one-way and two-way slab calculations are basically for hand calculation part, and one-way and two-way will always be limited to rectangular type of structure. For an irregular structure, you will have to theoretical answer. You will have to find out the yield line. See, usually all these yield line theories establish the cracking pattern. And once you put the cracking pattern in place, then you are able to see the distribution of a building. In the best case scenario, in a simpler building, you need to approximate any trapezoidal slab as a rectangular slab, having the average span going in that varying span direction. Best way, because now everybody has a software tool available with it, do not define it as a, go to a third software called as the Sieve Analysis, which comes along with the ETABS, and the Sieve, irrespective of it is one way or two way, by the finite element analysis will design the slab for you. So I would go by the safe way. But Sieve is the patented name of a software.
Very nice session. Very nice session from you, and feedback from participant is also nice. So we will send session is over for today's session, feedback session.
Yeah.
I again invite all the participants for tomorrow's session on design of slab by Madhav Chikoli from Mumbai. So thank you once again, Umesh Joshi sir. Very
Grateful.
nice.
Thank you very much and take care.
Okay. Thank you for all participants who have a part in this session. Okay.
Grateful.
Thank you very much.
Bye.
So here I conclude this session.
Thank you. Grateful.